Thank you very much for the opportunity to speak. I had an internship with Xeon, Xeon 2 years ago now, I guess, yeah. And what was nice is that we collected data and published within 1 year. So I'll be talking about some of that towards the latter portion of the talk. When we talk about an applied machine learning problem, there's actually this kind of neat allegory of 80% of the effort is cleaning the data, right? And 20% of the remaining effort is just complaining about cleaning the data. That's really the worst part. And I think what we need to think our problems are is getting the right data in the right form. And where does this come from? Well, there's the Kaggle survey in 2017. It's since been updated, but 240 or so scientists were asked in the manufacturing sector, what are their problems? And they all say the same thing: dirty data, and to some extent, lack of data science talent, because really there's so many problems that are interesting in this area, spreading, a lot of the opportunity out there. So the heart of the research that I'm going to share in the forthcoming slides is really working around these particular questions and asking the right questions that machine learning is appropriate for and getting the right data to solve them. There are these three case studies. Actually, there'll be a fourth. There are different additive manufacturing techniques that I'll get into in a short bit, but we break them down into regression classification problems. And the point that we can make here, and I think that is not hard for this audience to believe, is that these machine learning algorithms are versatile and can process data streams to make these decisions to help understand our process. So a really intuitive example is shown here. Automating microencapsulations with machine learning. So there's a process we care about at the lab in which you take these small droplets. You can put, in this case, carbon sequestration fluid in the middle of them, and you can create these droplets for CO2 sequestration. And there's four things that typically happen during typical operation. You make droplets that you like, or you have three other error modalities ranked in most common appearance here, where this green case is called wetting, and you can actually damage your device. This yellow case is called jetting, and you make droplets that are not the correct size. Or this last case, which is somewhat rare, these droplets break, and to be honest, there's nothing you could do about it. And what we do is train in a classifier and trigger a response. We built a Python-based controller that operates in real time and performs a sorting function on these droplets. So the neat thing that we did was collected data, images in our training set, and came up with an ablation study shown here that shows how the accuracy changes as a function of training set size. And also I plot equivalently training time. And what you can easily notice is, oh my God, 1 million images. Well, it's not quite the case. We collected 70,000 images. I personally labeled all of these. And through data augmentation techniques in which we change the darkness, rotation, blurriness of all the images, we find that we can get an algorithm that is not only more robust, but actually more accurate as well. My screen appears frozen. Can you see me still? Is the talk coming through? Okay, looks okay, great. And we actually deployed this in a real system and can sort rejected from collected droplets. And what we find is that basically the system works, and we can get higher quality material from this system. And we have published about this in actually two different journals, different aspects of it, and received quite a bit of attention. The neat thing is we are dealing with real data sets here. These are not balanced data sets. And what we did was have a cost function that penalizes rare classes in order to maximize our prediction of those particular cases. All right. And with this, I should say that the traditional approach to monitor these systems up to this point was actually paying some poor graduate student to monitor the system for 5 to 8 hours at a time, manually selecting or monitoring the process. So this is obviously an improvement in that, as you can all appreciate. Another case here is shown detection of direct inkwrite clogs. This direct inkwrite is a technique in which you extrude material. In this case, it's carbon fibers in a polymer matrix that print into a part. And what you're seeing on the right here is this ghost printing that happens, in which the clog has happened, and that happens sporadically. And what we can do is actually collect videos of this during real operation, do single frame labeling, and train a model to come up with 97% accuracy for the clog case and 99% accuracy for the unclogged case. And you understand that if you're analyzing a sequence of frames, your error goes as 1 minus the accuracy to the n number of frames. So actually, after 5 to 10 frames of detection, you basically are guaranteed 100% assessment of your system, accurately speaking. We actually took that microcapsules algorithm that I showed you in the last slide and threw it at this problem, and it worked on that too. We chose to go a different route, as I'll show in the next slide. But the point is we had one algorithm lying around. We attempted it. It worked. It just goes to show how the development time for these algorithms pays off when you can apply them to new problems. They're transferable. And what we wanted to know, though, was how well the algorithm decided, because there's possible biases in our data that we may not be aware of. And so this saliency map allows us, we borrowed Zhu et al. There's many ways of doing this now, but we looked at each pixel, ranked them in importance, and there's no units on this, it's model specific, but you can see where the algorithm is paying most attention to. And in this case, it's looking at the nozzle and the periphery to see if materials are coming out of it. Also, there is the activity map for the clog. It actually focuses just at the nozzle tip and nowhere else. And if that doesn't have motion or material there, the algorithm assesses it as a clog. And in published work on this, which I can share in the chat, we have we perform a confusion matrix to get to the bottom of how well we trust these algorithms. And furthermore, here is the paper shown on the bottom message. So switching gears a bit to yet another 3D printing process. This is a very popular commercialized process called laser powder bed fusion. You take a metallic powder bed, you shine a laser, high-powered laser wherever you want to melt material, and then after that layer is done, you add a new powder bed and repeat that process to sequentially or selectively melt into your parts, your part into existence. We have a very customized machine in which we can outfit all these bells and whistles and sensors. And in this particular case, the thing to focus on here, I'm presuming you can see my mouse, but it's the common focal point between the high-powered laser with a pyrometer, the camera, as well as an illumination laser. I may have not included it in this diagram. But what we do is we take this common focal point and raster it across the build plate as we build parts or laser tracks, and collect this data from the camera or the pyrometer and other sensing modalities to determine quality from these sensing from these sensors. And so what I'm showing you here is the process by which we link properties to the in situ video data. I'm showing you a bunch of laser track welds. These are each 5 millimeters long, created in a variety of conditions. We're varying, in particular, the laser power and the laser speed. And I want to know what was the quality of each of these parts, because I know particularly what data I collected. And in fact, you can take a height map scan of these track welds. This is a standard measurement tool that gives you the height of each pixel. I could go into that measurement if you're so interested. It's an interesting structured light problem. But in any case, what we did is targeting a particular example. We have a computer vision algorithm that distinguishes track from non-track. And from this particular track, we can obtain our measurements. In this case, this track has a particular width. It has a particular standard deviation. It is not continuous, or you can even argue what percent of non-discontinuity there is if I can compute how many millimeters of discontinuous parts there are, knowing that all tracks are 5 millimeters. And what we could do then is plot our measured values as a function of power for the various speeds. And in particular, and we have repeat data points too. So I'm showing you the standard deviations of our measurements there. And this actually wrapped up to a patent that is quite cited nicely, that demonstrates this technique, because you can sync it up with more than just video. But the point being is, for every particular laser track, we have video data, and that video data is now labeled. And now we're going to send this to a convolutional neural network that looks at this problem. And this is really in-process monitoring, which you can think of as a step in the direction towards real-time correction. Okay, so I'm going to walk through our architecture here, or in our data. We have a data set comprised of 870 millisecond to 10 millisecond videos, which, as I said earlier, are labeled according to track width, standard deviation of width, and track continuity. This is a modest data set, admittedly, but there's things we can do to validate whether enough is enough or whether we need to collect more data. We borrowed and modified a architecture available in the open literature. We didn't need to invent something new. And we could train on your standard research computer, your standard GPU box, to get results within 12 hours or so. And these predictions are generated in under 2.9 milliseconds, which is, to be honest, fast, but not as fast as we might need it to be to implement in a real-time environment. What we can do actually here is measure, plot our data points for testing and training data on a predicted versus measured curve. And in this particular format, of course, as you know, if all the points lie on the unity line, you actually probably have a data model that's overfitting the data. So you don't quite want that, but the R-squared value is 0.93 for width prediction. It's not as good for the standard deviation of the width prediction. And we go into great detail about why we think this is in the paper and what we could do to correct it. But furthermore, we can correct the classification accuracy on the track continuity. And I actually want to take a quick pause to tell you about our review process for this paper. At the time, right, 2018, applied machine learning in additive manufacturing, super hot topic, is still super hot. And we submitted this. We're really happy with our results when we just submitted the first bullet point. We felt, wow, regression is a much more difficult problem. The community will care far more about it. But actually, that was not true. The reviewer said, we don't care about machine learning. Well, there's other ways of already getting width predictions. This is just, your guys are just doing work to do work. But they say, if you can get classification accuracy with regards to whether or not a track is continuous, there are no known methods to do that. So your paper's rejected unless you can do that. You have 2 weeks to do it, is what the editor told us. But we were just simply able to switch out the loss function to perform classification, retrained, and within 12 hours got our new results at this 93.1% threshold. Having now a single neural network that could predict 3 different distinct track properties, again, is a demonstration of the versatility of these algorithms. And actually, we were fortunately awarded the cover in Advanced Materials Technology. So this is like a work we're really proud of and had kind of an interesting journey within the peer-reviewed process. What we also have, this is showing you using a semi-supervised approach in which this particular algorithm we adopted has the same supervised loss function, and the unsupervised loss function essentially looks for what appears to be the nearest data point from an unlabeled, for an unlabeled data point. It looks at the nearest looking labeled data point and just assigns it, ascribes that label so it can go on through training. The reason to explore these approaches because the cost of labeling is intense. And so we wanted to figure out, is there ways around this or ways of managing that? And in particular, what we did was took that label, that same data that we showed earlier, and pretended a larger fraction of data was not labeled. And actually, in every particular case, we found that our semi-supervised approach outperformed our supervised only approach, except in the limit of the nearly no labeled data, in which case, to be honest, both algorithms are kind of guessing. And applied to the classification accuracy, we also got very similar boosts in performance when using this particular architecture. There's a lot of other data that we had collected to that I alluded about. For instance, in addition to high-speed video frame data that we have collected along this track as we make it, we have pyrometer readings. And in the middle here, you can see kind of a really nice track on the left. On the left, you see a really nice track, relatively uniform in thickness and not and there's no discontinuities. And then we have a very dismal track here on the right, where you barely are making any particular material. You can actually see from the pyrometer readings alone, pyrometer readings giving you a measure of the temperature of the melt pool as the powder is melting. You can actually start to see in this reading that like these dismal pyrometer readings may be a quality indicator, a poor quality indicator. And we explore that in our follow-on paper, which we use cascade neural networks. And this has actually been a paper published, what is it, like 2021 now. So, okay, so last year, in which we take things like video camera features like the melt pool area or intensity and circularity. So these are just geometric factors. And we call those collectively a set of video camera features. What we can also do is look at the pyrometer reading, which is in a way not as easy to extract features from, although you'll see in the paper how we make use of that. Feed that to a downstream artificial neural network to predict things like what we care about, the single track width. And then that goes to further downstream neural network architectures to predict things like the standard deviation and furthermore the track continuity. These were like very complicated design decisions that we made. We got great results into it, but you know, the cons are that like there's so many different choices that one could make as a data scientist. But the benefits are we can leverage what we know about the system into this particular approach. For instance, we understood how pyrometer readings were probably more valuable at predicting things like power velocity, more so than they were single track continuity. And we actually, you know, used our scientific intuition to help build these models and increase our classification predictions. And the paper here goes into great detail about this. Not only is it a machine learning study, it explores the physics of this system as well. Now, Bernard here walked through a comprehensive data set that we collected of photo curing performed under different resins under different lighting conditions. So this is a technique actually not dissimilar to laser powder bed fusion, but as opposed to melting a powder bed, what you're doing is reacting a photo curable polymer. Where you shine light at a sufficient condition, you will harden that material. And what you're seeing here is a variety of videos of this process happening. In this particular case, what we changed is the laser power and the laser speed. We also do different structures, like I had said, and also different materials themselves. And what you can start to see towards the end of this video are these small bubbles that form. Actually, when you put too much, there's too much of a photoreaction, you produce oxygen. That oxygen doesn't diffuse away and you get a bubble that leads to a defective part. And when people are optimizing this process, they're interested in different materials. They're interested in operating their equipment at the fastest possible operating conditions. So they want to the sweet spot where you get a part that is cured, but it's not over cured and it's not under cured. So you want this Goldilocks region, but that depends on the structure you make, the material you make, and your overall system. So we collected routine data. And poor Bernard had to label all this. I think it took him probably many cups of coffee and maybe like 2 solid weeks of effort, but we came up with this beautiful data set that's openly available to the community, shown here in this data in brief with 2020. It already has quite a bit of citations. What's nice is that we got the paper about the data published independently of the paper of the actual work. That is exciting. And get like practically double the publication. So I really recommend this route. Plus the community needs open data sets more than you realize, because I think like there's other things that we could do with this, and making it available to the outside world helps grow this area. So this labor intensive labeling process, like I had said, labeled 2 types of labels actually. In this particular case, the laser power is insufficient to cure a part. So we have an uncured label. Every single frame shows an uncured part, and also the whole sequence of frames allows us to label this as uncured. What's more is we now have in the Goldilocks range a part here that we're curing, and sometimes there's uncured steps in a quality part, but we call this one cured. And there's this boiled or damaged part, like I had mentioned earlier, where we can see, in fact, these bubbles get trapped within the part. but you sometimes don't see it in the final part, which is an interesting feature of this, interesting complication of this system. But this would be then a part level classification that would be basically a defect. The paper shows in detail how we provided frame-by-frame classification rates of about 95.3% and structure level classifications of 96.3%. And the implications here, I really want to spell out. Frame-by-frame labels allow us to monitor our process as we're building a part. So you can think of the labels on the left yielding a in situ monitoring process. The labels on the right help us determine quality of an overall part. And in this case, it helps for, in a way, parameter sweeping if I have new candidate materials that I want to work through. Okay, so I have a final slide here. I think I'm at time, but I just wanted to highlight how we're performing applied machine learning in a variety of additive manufacturing settings, ranging from scientific machine learning applications where we understand more of the model, so it's less black box, more gray or more transparent, through other models that leverage different data modality streams to come up with in situ detection. And so, Zian, I'm not sure if I should leave my screen shared or not, but anyway, I'm open to questions at this time.
Great.